The opinions expressed on this radio station, its programs, and its website by the hosts, guests, and call-in listeners or chatters are solely the opinions of the original source who expressed them. They do not necessarily represent the opinions of Revolution Radio and freedomslips.com, its staff, or affiliates. You're listening to Revolution Radio, freedomslips.com, 100% listener-supported radio, and now we return you to your host.
Welcome back to another episode of Cosmic Catastrophe on Revolution.radio. I'm your host, Diamond, and my lovely co-host, Leah Shaper, is joining us.
Hello.
With her mic on. We're going to have a fantastic show today. We're going to answer a few questions, or maybe be left with more questions. Do sun-diving comets trigger coronal mass ejections? That's the first question. And if so, can we explain Miyake events as cometary encounters with our sun? That's a pretty good title.
It is.
You looked at all of the information. Now, there are a lot of correlations we're going to bring to you in the next hour that are pretty mind-blowing. I'm going to save some secret ones for the second half. But first, we're going to just broadly go over what Miyake events are. They've been recently named and have been known for a long time, several of them, but it's only when it came into the forefront maybe a decade ago that dendrochronologists and other scientists dove back into the information, meaning the existing wood, and took a look again harder at the isotope data. So what happens during these Miyake events and how they're recorded on Earth and why we have such a good record of them is because of trees. And what happens during these events is that on Earth, there is a spike in beryllium, beryllium-10, carbon-14, and chlorine-36. All of these being associated with potential cosmogenic sources. So supernovas, solar flares, comets. You can also get spikes in some of these like beryllium from large volcanic eruptions. Mm-hmm. And more importantly, then becomes the complex question of what's happening on Earth with the weather blowing around all these isotopes and things like that. So Miyake events are categorized as massive solar storms or solar proton events, super energetic particle events. That's a good way to say it.
Typically, solar proton event. Seems to be the catch-all.
Okay.
Is your speaker near your mic right now? I'm echoing.
Nope. I'm pointing it all away.
Strange.
Yeah, I can't hear the echo.
I don't hear it now.
So let's share the screen and let me know if you can see it.
Yes.
This is a beautiful example of a sun-diving comet. It's quite a large one.
Yeah.
Most sun-diving comets are, a tenth of this luminosity when we see them. We see them quite often, maybe every month or so. Not all of them cause coronal mass ejections, but in the last decade, there have been several that we've witnessed that as the comet approaches, a coronal mass ejection occurs on the opposite side of the sun, as if it's a cause and effect.
Right.
Now, what's interesting is that in 2000, this is from 2011 here. In 2008, there was a paper that was written explaining this phenomenon. Explosion of sun-grazing comets in the solar atmosphere and solar flares. And then a few years later, this happens. So it's almost like, wow, it's really happening. But just shortly after this event, obviously scientists are on both sides. This came out. Did comet cause a solar explosion? Hardly, experts say.
Yeah.
So we've got two sides of the coin here.
Well, two things that are funny too is that 2008 paper, while it does sort of explain the phenomena, it's still talking about comets sublimating as they approach the sun, as if they're made of ice. Now, they acknowledge that the amount of energy released in the approach to the sun doesn't match like a simple sublimation reaction, let's say.
No, but let's say that comets
that there
aren't
has to be
ice.
plasma involved.
Let's say comets are not ice and they're electrical phenomenon.
Right.
which
Right.
makes them comets and have ion tails. What if it's the electrical interaction with the sun that causes the effect?
Right. So, I mean, so basically what they did is that they presumed that sublimation was still happening, and then they went, oh, there's too much energy being released, so there must be plasma involved. But, they found their equations to work and everything, but what they really could do is rewrite their equations entirely for an electrical plasma kind of interaction.
It's almost like they indirectly disprove the icy snowball theory.
Kinda, yeah. It's funny. But then the stuff being written several years later about, oh, no, it's just a coincidence that CMEs occur sometimes when there are sun-diving comets is absolutely hilarious. I mean, the reasoning is so childish, it's not even funny.
Not only is it childish, but it's not science. They're claiming definitively there is no reason to think the two events are related.
Right.
That's insane.
Yeah. Well, here's my favorite
science
quote.
Is settled. It's settled.
Right. This is my favorite quote from this article, and this was written in space.com in 2011. And this is a quote from Carl Battens, who was at the U.S. Naval Research Laboratory. And he says, I'm lucky enough to be surrounded by some of the best solar physicists in the world, and none of them can think of a reasonable mechanism in which physics would allow this event to be initiated by any comet, let alone such a tiny one. And so basically what this whole article says is like, well, we can't think of how this might work, so it must just be coincidence. How about reevaluating your science?
Well,
how about reevaluating whatever model you're using in terms of how this happens? It's freaking hilarious.
Right. It's been decades now since we've collected samples from comets and landed on them. There is no ice, and yet every single person in the field is teaching their students that comets are ice, dirty snowballs.
Right. So I guarantee
the tails that are being produced. It's so ridiculous. The tails are being produced by sublimating ice that isn't there. And then secondary tails are being formed by cryovolcanoes, ice volcanoes that don't exist.
If you haven't seen it, go back and watch the episode where we talk about that. It's hysterical, right? So it's the difference between water vapor and plasma, two completely different things. And this guy is like, oh, well, all of my fellow scientists, we can't think of a mechanism, but that's because you're not considering that comets are electrical.
Yeah.
Hello.
The sun is electric. This comet is electric. It's causing an electrical discharge, just like anything that with an opposing charge would have. And it's barreling towards this gigantic, albeit it's tiny, it's barreling towards this giant volatile electrodynamic plasma ball.
Right. And nothing's going to happen.
Everyone knows what happens when you just put your fingertip on a plasma ball that you buy at Spencer Gifts, right?
Yeah.
The plasma comes towards you.
Yeah.
So some kind of a cause and effect is happening here.
Right. And so the best that they've done is they've said, well, there's no correlation because sometimes sun-diving comets don't produce CMEs.
Of course not.
That's the basis of their reasoning. That's it.
And because they're not using an electric universe model, which would explain it, obviously some sun-diving comets don't have the correct charge to create this discharge.
Sure.
And that would be the reasoning.
Yes, exactly.
Yeah.
It's pathetic.
So it's because their model doesn't allow for an explanation that they can negate it.
Yes.
And scientifically speaking, I think that's a very weak position to have.
And even if, the fact that they're not even considering that they have the wrong model, that's the thing, is that when you say something like none of my fellow scientists can think of a mechanism which would make this possible, that is the clue that should tell you that your model is wrong and that you need to look at another model. That's the trigger, right? But they're not doing that.
Right. And the last decade, since we have the James Webb Space Telescope and all this new equipment, scientists in the field of astrophysics are constantly baffled.
Yes.
By everything.
It's pretty funny.
And in fact, in their static Big Bang universe that they calculated to be 14.8 billion years old, they just doubled the age because they were able to look 26 billion light years away.
Yeah.
Which means their Big Bang model is incorrect. But it can be correct because remember, the Big Bang model suggests that the explosion is traveling faster than the speed of light.
Right.
Which is impossible, first of all, using, yeah. So the explosion is faster than light itself.
Yeah. Well, I love too that it's like the reasoning is based on our own capabilities. Like suddenly we're able to see further via this telescope. And so therefore our conclusions have changed. Like that doesn't make any, that's not scientific. That's not how you do science.
How do we fix this, Jimmy? Let's double it.
Right. I mean, the better, least difficult thing to do would just be to say, we don't know. Like, that's not a terrible thing, right? Like, it's actually good to be able to say, I don't know, because it allows you to look at a lot of other explanations, not to mention that it's much more honest.
Right. Now, here's the double whammy and why we're going to bring Miyake events in here. Because what you're looking at here is two of the major sources of beryllium spikes and carbon-14 on Earth, comets and solar storms. And so in this picture, you get a double cocktail.
Yeah.
So the idea is a large cometary body, which is not just the comet. And I think people out there tend to not understand this. Like Comet Swift-Tuttle, which may be the explanation for the Charlemagne event, 774, has a periodicity of 133 years. Every 133 years, it comes in close proximity to the Earth and the Sun, and then goes back out on its journey. It does not always follow the same path. It has a cyclic motion where it's further and closer, and in its path are billions of tiny objects that are in tow. And that allows the comet Swift-Tuttle to cause a meteor storm here on Earth every 133 years. And so the suggestion would be that there's comets out there that at one time or another get close enough to the sun that lots of pieces, I'm not talking one like this, I'm talking dozens or hundreds, pummel the sun, and coronal mass ejections occur in every which way. Also, you would have pieces maybe coming in contact with our atmosphere or hitting Earth, small pieces. And that cocktail, so these Miyake events show carbon-14 and beryllium-10 spiking for a year or more. And so that is why it's like unexplainable, because it lasts so long. But if it was such an energetic event and multiple pieces were hitting the sun, the solar storm could last for weeks or months. Right. And then those isotopes would blow around for an entire season.
Right, right.
So it's a good explanation for what these events are, in my opinion.
Yeah, yeah. I want to throw in one little detail here that I picked up in this paper that we're going to look at, which is they make a very important point that with beryllium-10 tends to be attracted to aerosols, and so it precipitates out within like 1 to 3 years, whereas carbon-14 tends to persist in the environment for much, much longer. So I just want to throw that out there preemptively, because I think you can make some distinctions with that about what's going on.
And so any spike in beryllium then would express on Earth for a period of years, no matter what it is, based on what you said?
No, like it would be up to like 3 years.
So it could be a 3-year spike because it takes that long to precipitate the beryllium out.
Potentially, yeah. Whereas the carbon-14 can persist, right? So you may see some differences in the data there.
Okay, that's interesting to note about because of a point I'm about to bring up.
Okay.
That what we know about Miyake events, we currently know we currently know of 9 since the Holocene warm. Since 14,400 years ago, meltwater pulse 1A, and we'll get to that. Nobody can explain what happens at meltwater pulse 1A to bring sea level up 60 feet, 20 meters, and it just so happens to correspond to one of these beryllium spikes. In fact, it's the most energetic Miyake event out of the entire group. Now, the problem is we don't have much wood earlier than 15,000 years ago. It's hard to come by. Yeah. But we have a continuous record from about 15,000 years to present, which is amazing.
Yeah, yeah.
So we've got the Well, let's go. These Miyake events are solar storms, very much unlike the Carrington event. The Carrington event would be like a baby version of this. These events can be 10 to 100 times more energetic than an X20 solar flare. So that would be like an X100. It would be unimaginable and probably pretty rare. But in fact, these events happen on a periodicity of about 1,000 years. 12,350 BC, 7176 BC, 5410 BC, 5259 BC. And then there's a lull. Then it's 660 BC, 774 CE, 993 CE, 1052, and 1279, which means the next Miyake event is due.
Like overdue.
Yeah.
By a lot.
So, and not all these events are the same. There are 5 standouts: the 7176, the 5259, the 660 BC, and the 774 CE and 993 CE correspond specifically to massive carbon-14 spikes. The other ones don't. They're more beryllium and chlorine.
Mm-hmm.
So there's 2 different types of Miyakes. And I propose that one of them, maybe cometary particles are hitting Earth at the same time, and in the other one, it's just the sun.
That's what I'm thinking. And that's sort of why I raised that point, right? That the beryllium-10 spikes by themselves may indicate close proximity to a comet, whereas when you see beryllium-10 and carbon-14, perhaps that's the Miyake event.
Yeah, and so it doesn't necessarily have to be that a piece hits Earth. These comets have tails, and we could literally be interacting with the plasma tail.
Yeah. The other thing that would be really interesting, and I don't know if we're at any level where we could really look at this, is that supposedly the beryllium-10 is a bit more localized, like particularly because it is bonding to aerosols and precipitating out. So it would be interesting if
you'd have to do a geochemical study of all the dendrochronology across the Earth.
Exactly.
Wow.
Exactly. So I don't think we're there. I don't think we can. I don't know that anybody's really doing that kind of work. That's a massive amount of work.
It certainly could be a PhD study.
Yeah.
Now, just for background, there's strong evidence that Miyake events are caused by extreme particle events. And so that is the one we were talking about, where we've got comets, that lots of cometary pieces smashing into the sun, creating this forced solar storm. It's a forced solar storm. It wasn't going to happen until these little buggers started interacting with the magnetic field of the sun. Maybe dozens or hundreds. And so the sun just goes boom, 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 boom. You get all these cannibal CMEs coming towards Earth, and the effects on Earth would be horrendous.
Yeah. By the way, I have to remark on this image. You sort of said it earlier, but I'm astounded by the size of this comet that we're looking at here. It's
a pretty big one. I think that would be miles wide.
It's huge. I'm just like thinking, again, relative to the sun.
The luminosity is not indicative of the size.
Understood, but still.
It's a big one because I've shared with you other sun diving comets, and they're literally pinpricks.
Yeah, exactly. Yeah.
All right. So interestingly enough, I think that AI has a great purpose in these podcasts for us. Because I found that Bard AI is very concise when you need to scrub all the scientific literature and you don't have time because there's 9,000 papers. You ask it to do it for you.
Oh, wow.
And it does some pretty concise. I asked some pretty interesting questions, like what is a Miyake event, just to test.
Yeah.
And it nailed it pretty well. Then I said, can sun diving comets cause Miyake events? And Bard AI says this, which is fascinating because it's our position. The potential link between sun diving comets and Miyake events is a fascinating and complex topic with ongoing research and debate. And here's what we know. And it goes on to describe Miyake events are extreme geomagnetic storms, significantly stronger than the average storm, occurring every few thousand years. They can cause widespread disruptions to Earth's magnetic field, leading to auroras at low latitudes, radio blackouts, and potential damage to infrastructure. Evidence for Miyake events comes from tree rings, ice cores, and the Japanese historic records. That is insane that it found that little tidbit.
Yeah.
And then it goes on to describe sun-diving comets. When these comets come close to the sun, their icy surfaces vaporize, releasing large amounts of gas and dust. So this is the bias of mainstream science in AI.
Yeah.
But no mainstream scientist would say the first sentence, which is why I like this bard.
Mm-hmm.
He thinks that the link between sun-diving comets and Miyake events is fascinating and complex.
Rather than just denying that there could be a link at all.
Exactly. In conclusion, AI says the possibility of sun-diving comets causing Miyake events remains a compelling but unproven hypothesis, and further research and observation are needed to definitively establish or disprove this connection.
You know what's really funny about this is that the AI here is far more honest than the scientists. From that 2011 article.
Now, there's tons of accounts of these happening in historical context. I brought this up. It's interesting to note that prior to the main Miyake event, which is called the Charlemagne event, and the 660 event, there are accounts of aurora, but they do not correspond with the Miyake events.
Mm-hmm.
So here's 633, 660 BC we're looking for, but this is all AD right now.
Mm-hmm.
And the 774 carbon-14 event is not really here. There's a 773 June Friday.
Mm-hmm.
But in the Japanese bamboo books, we shared that before. There's an exact 774 account of a weird thunderstorm and some other strange things. Remember?
Yeah. Yeah.
So I want to focus on, in the second half, let's bring it together here. The largest of these energetic events I think we should focus on is the enormous Miyake event, which happened 14,300 years ago, which in a recent paper is corresponding exactly to meltwater pulse 1A.
Mm-hmm.
And also in the second half, we'll bring it together, is that these events, all of them, correspond to warm spikes in the Holocene. They all correspond to the top of these peaks when they occur. So there could be two things happening. These peaks are solar maxes, where after a period of cycles, you reach a solar max like we just did in 2016.
Mm-hmm.
And during the solar max is when you're going to get the most solar storms, correct?
Mm-hmm.
So if it is a naturally occurring event, because it's happening at solar max, makes sense. And the last solar max, we didn't have a Miyake event because it didn't get that hot.
Yeah. Yeah.
So that could be one explanation.
Yeah. Well, also interesting too, in this, I mean, we'll get to this, but in this paper, it also talks about there's like 100-year period between 14,300 years ago and 13.9, where you have excessive carbon-14 and beryllium-10 again for like a century. Now, their hypothesis is that this may correspond to a solar minimum, and that might be why, like a grand solar minimum, but it's interesting.
And increased cosmic rays because of low solar activity.
Exactly. Yeah.
Yeah. And so as we go into the second half here, this is the paper that brought it to my attention here when these new dates came out on, see, meltwater pulse 1A had been contested on when it occurred, and now it's narrowed down to 14,600 to 14,300 years, exactly when this Miyake event is occurring, and that is a very close correlation. Now, correlation is not causation at all. But when we get into the second half and start looking at the correlation with temperature spikes in the Holocene with these events and magnetic excursions happening at the same time, there could be a multiplicity of things happening causing these spikes for many years.
Yeah.
And as we leave here, the most significant, this yellow stripe, is that 14,000-year event.
Mm-hmm. Mm-hmm.
Pretty fantastic.
And it's such a huge spike too. I mean, it blows everything else out of the water as far as Miyake events are concerned.
So then the big question is, are these Miyake events what is causing the ice age cycle?
Right.
Or
Are they separate?
releasing us from it every 105,000 years?
It's funny. One of the things that really strikes me, and we'll get to this, but is that this particular Miyake event, it precedes the end of the glacial period, right? Like we have this long stretch afterwards where we stay warm, but it's almost like it happened too soon. And then it gets, the Miyake event happens, it gets warm with the bowling alley rod, the temperatures drop off again, and then we get warm again later. It's very interesting. It's like it was out of sync or something.
I think the Younger Dryas event is an aberration. We should have kept warming.
Right. Yeah. No, that's the impression I get too. Yeah, maybe
something slammed into the ice sheet and all hell broke loose.
Yeah. That's a better way of looking at it, I think. Yeah.
And because it's in such close proximity, it might still be part of the parent body of this cometary object, which whatever it may have been.
That's also possible. Yeah. Except that one produced a temporary warming and the other one produced a permanent one.
That's interesting. What's also interesting is that there's no commercial coming up and it's already 3 minutes late.
Huh. That's bizarre.
Maybe we won't get one.
Maybe we won't get one tonight. That's bizarre. Oh, and we're still, the server is still in the call, yeah?
That's a good point. Yes.
Looks to be.
Yep.
Huh. Very interesting. Okay, well.
Well, let's jump over to Meltwater Pulse 1A. This is the name used by quaternary geologists, paleoclimatologists, and oceanographers for a period of rapid post-glacial sea level rise between 13.5 and 14.7. We now have narrowed that down to 14.3 to 14.6 years ago, during which the global sea level rose 52 feet and then 82 feet in about 400 years. That would have been a scary time because the majority of the population, 80% of it at any given time, lives along the coast at sea level.
Right, because why wouldn't you?
So 80% of the population was inundated over a period of 300 years.
Yeah. And here we are freaking out about modern global warming. It's funny.
Yeah. 52 feet, then 82 feet is pretty crazy.
Yeah. Yeah.
Now, it wasn't instantaneous. It wasn't like they woke up underwater, but the water kept coming and it never stopped. And people that were alive for like 50 years would have seen the water rise 10 feet.
Yeah.
So it would have been quite spectacular.
Yeah.
What else is interesting is to consider the fact that humanity at this time is witnessing all of this. The dynamic changes on Earth are so epic during this time, it must have been unimaginable. Yeah. And so it's also coinciding with Miyake events. And if these events are the largest, 100 times bigger than the Carrington, imagine what they were seeing in the sky as the sea is rising. And it's just, it would be very scary, I'm sure.
Mm-hmm. Mm-hmm.
And so here you can see that Meltwater Pulse 1A. It is the first rapid pulse from the last glacial maximum, literally.
Mm-hmm.
So the bowling alley rod happens, the warming starts happening, and the sea level rapidly rises.
That's a very steep slope there.
And you can see what happens during the Younger Dryas event. It's only like a small stoppage of sea level rise. The sea level doesn't fall, the temperature falls. And because the temperature falls, sea level stops rising.
So, okay, I see, yeah, because it's just that first little sort of flat, nearly flat area that would be the Younger Dryas, right?
No, this is called the first Dryas.
Oh, that's, okay.
Then this is the Younger Dryas.
So it's the older Dryas over here, and then
and then this curve is the Younger Dryas event.
Okay.
Something hits, sea level goes up rapidly, and then it stops because it gets very cold.
Mm-hmm. Yeah.
And then we've got that 11.4 date when everything goes back to normal. and sea level continues to rise.
I mean, it's so obvious from a graph like this that something very abrupt is happening. I mean, just look at the the change in that slope.
Yeah, and the data is pretty good. They have it from at least 4 or 5 different. They have sea level data from 4 or 5 different locations worldwide. Because you can easily you can find the ancient shorelines where there are shorelines.
Oh, well, I mean, just the graph that you were showing previous shows that there's many sites being used.
Oh yeah, the dots.
You know, there's more than 5.
Okay, duh.
Yeah.
Well, but they don't all overlap.
No. Okay. Fair enough.
So you got to link them together like tree rings.
Yeah. Yes.
All right. So let's talk about the dating of these events. Now, interestingly enough, I found a paper here on the Eemian worm. Or if I can scroll all the way up to the top here. There is a beryllium-10 climate fingerprints during the Eemian in the ice core in Greenland. Now, what they use beryllium-10, there's no spike here, but they're using beryllium-10 as a proxy for temperature. And what they found is that the Eemian average beryllium concentrations are 0.7 times lower than the Holocene ever, suggesting that it was much warmer than now. And they're claiming that it's the hottest year ever.
Yeah.
So,
right. Which is easily disproven, but anyway.
I know, and that brings us to this graph, which was because of the Michael Mann hockey stick, the Minoan worm, the Roman worm, and the medieval worm have been erased from humanity, literally scrubbed from the data set.
Yeah. By the way, I like the fact that you always say shtick instead of stick. It's like a shtick because it's a scam, you know?
Oh, and it is a scam. I feel bad for Brian Rouge.
Do you really? I don't.
We've never had a non-bumper. So a couple things that I want to bring to your attention here as we move forward is simple. This is raw data, and it is not adulterated. It's not homogenized or corrected for anything, especially for the IPCC.
Right.
And what you will glean is that atmospheric CO2 has nothing to do with temperature.
Yes.
In this time scale.
Clearly.
Yeah, that's kind of funny.
Yeah.
Now, where is the Epica data? And here we can see CO2 and temperature laid over each other. I did have, okay, this is what I wanted to bring to your attention. Take a look at the lowest CO2 ever in Earth's history. Right here. It was about 18,000 years ago. And we almost hit 180.
Yeah.
I think it was 182
which means that we almost all died.
The whole planet almost suffocated.
Yeah. And then we hit that level like again and again and again. I mean, we're pretty close, like all of the other minimums here on this graph.
Yeah, that was particularly low.
Yeah.
I think below 180 and it starts to die. 150 is cut off and everything's dead.
Yeah.
So the fact that we need CO2 is more important than ever. And the climate scam really needs to stop.
Yeah.
All right. So we've got an event 14,300 years ago, the largest Miyake event ever recorded. And here we are looking at the magnetic field intensity for the last 300,000 years. And right at 14,300 would be right here to the right of the yellow line, which would literally be, take a look at this, in the center of the massive drop in field strength.
Yeah.
So do Miyake events cause geomagnetic excursions? Do they accentuate them?
Yeah.
Because look, this geomagnetic excursion is rapidly occurring, then boom, the Miyake event happens.
Yeah.
Could the geomagnetic excursion allow for cometary bodies to potentially be at greater risk for hitting the sun?
That's a good question. I mean, because you're comparing sort of apples and oranges here, right? Where we're talking about magnetic excursion on Earth versus what's going on with the sun at that moment. I mean, I would certainly say that it certainly makes us, any excursion obviously makes us more prone to receiving cosmic rays, and probably also from to getting bombarded with stuff. So it's hard to exactly make the connection to what's going on the sun at that moment.
Yeah, it's definitely an interesting correlation.
But something definitely happened at 14.3, right? I mean, this massive carbon-14 and beryllium-10 spike is huge. I don't know if you have any of the figures from this paper that you sent me.
The 14.3 paper?
Yeah. So this was published in the Royal Society? Yeah, the Royal Society.
Where did it go?
This year. And
yeah, I got it.
If you look at, let's say, like figure 9 is a good, easy one to look at.
Tell me when I'm at figure 9.
Huge. Huh?
Tell me when I'm at figure 9.
Hang on.
Is this it?
No. Nope. Nope. Keep on. That's not quite the one I'm thinking of. This one. Yeah.
Okay.
Yep. Yeah. I mean,
there's the spike.
Giant carbon-14 spike, giant beryllium-10 spike.
Simultaneously.
Really fascinating. Huh?
Simultaneously.
And by the way, you see that too at 13.7.5. Yeah. Also huge. Not as big as 14.3. And then you also have like this 100-year period from 14,000 years before present to 13.9. You've got a long period of time where you have excess beryllium-10 and carbon-14. So it's not just a spike, it's like persistent. Yeah.
I wish they gave us more of this graph. It's a very short time frame there.
Yeah. Yeah. Well, because the reason is because this is the time period that they looked at, right? So they looked at a very large number of trees in this region in France that were subfossilized, and analyzed what they got out of those trees, and did very extensive analysis in the sense that they went to great pains to calibrate the radiocarbon dates and compare it with dendrochronology, where we have absolute dates because of previous analyses that were done. I mean, they did a lot of analysis in this paper to really make the data as accurate as possible, and sort of kept coming to the same conclusion again and again.
This is interesting, the 13,960.
Yeah.
What do they say about that?
Well, this is part of that 100-year spike of carbon-14 and beryllium-10.
So we've got the major eruption of Locker C happening just before the Younger Dryas event.
Mm-hmm.
That could explain the beryllium.
Right. Right. I mean, it's obviously a different kind of event than the sharp spikes that we see at 14.3 and 13.7.5.
Yeah, it's like 40 or more years. It's long.
Right. Right. So this is probably a different kind of event. Like I wouldn't call this a Miyake event, and I don't think they would either.
Right. And the Locker Sea erupted for decades.
Right.
So it could be a volcanic eruption there.
Yeah. But well, yeah, no, that would still work. I was going to say, because you also have to consider the fact that beryllium-10 doesn't really stick around that long. But if you have a continuous eruption, then you will see it persist in the environment.
The source of meltwaters for Meltwater Pulse 1A and the path they took remains a matter of continuing controversy. The debate is centered around whether the predominant addition to sea level rise came from the Antarctic ice sheet, the Laurentide ice sheet, or the Fennoscandian and Barents Sea ice sheet.
That's hard to say.
Yeah. Interesting.
Yeah.
But what, in your opinion, this is a good question. So we have this Miyake event. There's a huge solar blast. There's multiple solar blasts, huge solar storm on Earth. What's causing the warming?
Right. Well, so that's the question, right? Like, is it that this was a Miyake event that was so large that you had huge amounts of radiation that were just persisting in the atmosphere and therefore causing warming? I mean, I think that's actually a pretty good possibility, because if you look at the temperature record for this period of time, you do get warming for a while, but then it falls off, right? And then we end up in the older Dryas. I don't know. What do you think?
Well, it's my best hypothesis to suggest that because of what we've seen up in the Arctic with mammoths being flash frozen 42,000, 32,000, 38,000, 22,000 years ago.
Mm-hmm.
I think some are 14,000 years old. That it was a long period of bombardment on our planet.
Mm-hmm.
Cometary pieces were hitting multiple times.
Mm-hmm.
And the end game was that 12-8, 12-9 Younger Dryas event when all the rest hit.
Mm-hmm.
And so what we also have evidence from about 15,000 to the Younger Dryas event in that time frame. Not only do we have this Miyake event, we've got the Channel Scablands in the Pacific Northwest formed in that time frame. So we need to have multiple massive floods happening from the Laurentide ice sheet at that time. It's so massive and it's so thick that a couple of things hitting it are not going to melt the whole sheet.
No.
The whole sheet only melts until the climate is affected. So much fresh water hits the oceans that something switches.
Yeah.
And in the case of the Younger Dryas cooling, what that would happen is there would be a massive freshwater influx into a so Earth is rapidly warming through the Bowling Alley Rod. This Miyake event may have accentuated the warming.
Or maybe it was the trigger.
Could have been the trigger. And what that's going to do is that's going to really turbocharge thermohaline cycles. So ocean currents during this massive sea level rise and warming are going to be kicking on in a huge way. And the climate is going to completely change. It's going to push warm air up into the cold areas, just like we have today. And the whole Earth is going to shift like we see. And then the Younger Dryas event happens and it shuts down those circulations almost overnight.
Yeah.
Because trillions of gallons an hour are running into the ocean. And it basically, it's a mini ice age for 1,400 years.
Mm-hmm.
But all ice ages must come to an end, correct?
Yes, apparently.
And so 11,500 years ago, there was another massive right here. There's a magnetic high and low. There's excursions happening throughout this event. Yeah. So for some reason, we have a spike at 11.5. It's actually at this low. It's during a magnetic excursion, and let's, this really is not going to help us here because it's just bringing us up into the current. I need some more graphs here, darn it. Let's go into a little high resolution magnetic field on Earth, see if we can get a better graph. I love this paper.
Yeah. Yeah, it's a great paper.
Yeah, so and at all these times, 11.5, 12.9, and 14,005, they're all mass extinction events too.
Yeah, yeah.
And that's probably just related to such massive climatic shift where animals can't move to an area that they need to move to.
Yeah, yeah.
And so what's weird is that in all these mass extinctions happening from 14 to 11.5, they've gone back to blaming it on man.
Again, it's like super childish, right? Because obviously based on everything that we've just talked about, you know, we're talking about solar proton events effectively causing Miyake events. We're talking about ocean currents changing. We're talking about melting ice. There's magnetic excursions. There's so many different things going on here that apparently that they don't really want to do the science because it's complicated. So we'll just blame it on humans.
Bard AI, when I was having a conversation with it, said the only way that we'll get to the bottom of Miyake events is with a multidisciplinary approach incorporating geology, geography, history, and astrophysics.
Well, Bard AI is correct in that respect. Yeah.
All right, we've got about 10 minutes here, no commercials yet. Let's go through all the Miyake events and the Holocene temperature record. The most recent event is 1279, which is right about here, which is in the medieval warm period.
Mhm.
And on this graph could explain here is 1279, explain the warming.
Yeah. I mean,
All right.
fascinating, right?
Yeah. Well, actually, no, 1279 would be on this side, wouldn't it? This is
No,
years
other
before
side.
present. So 1279 is only 800, is
Oh, years before
780
present.
years ago.
Oh,
So that could be, that's the spike right there, 1279. 1052 is this top of this.
okay. Okay.
Then we have 993, which would be still in the medieval warm, which is interesting. The medieval warm has two Miyake events 60 years apart. All
Maybe
during the,
maybe that's partially contributing to keeping it warm.
Yeah. So 774 would be, where is 774 on here? It's right there during this spike.
Mm-hmm.
It's hard to
Interesting.
tell. It's hard to tell.
Yeah.
Then we go to BC. 660 BC. There's a spike here.
Mm-hmm.
5,259 BC would be 7,257 to 50. Well, that's right here. Look, 72 is again at the bottom and the beginning of this spike.
Mm-hmm. But then, like, okay, what happens at roughly 3,300 years before present? What's going on there? I mean, that's a huge spike in temperature.
3,300 would be
I'm not good at doing this off the top of my head, so
it's 1,300 BC eruption. The Minoan eruption. It's actually, that's 1,600 BC. Where are we? So 2,000. Yeah. So the Minoan eruption causes the Minoan warm. Here's 1,600 is right here. That's at the bottom of this spike.
It would be so great to see this overlaid with carbon-14 and beryllium-10 spikes.
I bet you we could do that in the next episode.
Yeah.
And I suspect that a lot of these spikes are massive volcanic events.
Yeah.
All right, let's check out 9,176 years ago is right here. That's a massive Miyake event.
Mm-hmm.
Another spike. And we don't have it on here, the 14,350, which we've already talked about.
Mm-hmm. Mm-hmm. And then also 8,000 years before present. So roughly 6,000 BC.
No. Yeah, 6,000 BC. 6,000 BC warming.
Because that's enormous. Because there's obviously a big dip right before that.
When equatorial weather patterns may have reached further north than at present, the westerly storms, that's not really going to help us. 6,200 BC. What was the climate crisis? The 8.2 kiloyear event was a sudden decrease in global temperatures that occurred at 8,200 years before present, which lasted for 2 to 4 centuries. And do they have an explanation for it? There it is. There's the low. We were asking about the high. A rapid cooling was identified by Swiss botanist Heinrich Zola in 1960, who named the event the Missoy Oscillation. And these sedimentary records, the cooling event, may have been caused by a large meltwater pulse resulting from the final collapse of the Laurentide ice sheet. Oh, so the last this is like a mini Younger Dryas again.
Yeah.
The last chunks stop this thermohaline circulation, and then the sun's got to heat the ocean up again and get it kick-started.
Right, but then we have a major warming spike right after that.
Well, as soon as the thermohaline circulation happens, it's going to get very warm.
Yeah, okay.
That's why it's warm in Europe.
Yeah.
But if we turn off the Gulf Stream, the Europeans are going to be pretty unhappy.
Yeah.
It's interesting how we can explain all of these complex processes, these massive climate shifts through natural processes throughout the entirety of geologic history. Now, we don't necessarily know what's driving it, but if you just look at this graph, the variability is 4 degrees C regularly.
Yeah.
On the centennial and millennial scale. It's not on a geologic scale. And the entire population on planet Earth has been duped to be scared about one of the smallest shifts that we're looking at here in the last 10,000 years.
Well, I mean, the most absurd part of all of this is if you're going to claim that human beings are responsible for these sudden, abrupt warmings or not abrupt warmings, then you also have to say that human beings are also responsible for sudden, abrupt coolings or gradual coolings. So what's the explanation for that then? I mean, that's literally what you have to do, because when you make that claim, when you come to that conclusion, you literally are removing all of the other variables. So then human beings also have to be responsible for the cooling. So that's completely absurd.
Moreover, the lie is in plain sight here. When you're looking at this raw data here, the consensus, even with global warmists, is that the average global temperature is only 1 degree C higher than pre-industrial times. That means right here during the mini ice age, right here at the bottom. If we are only 1 degree C higher than the bottom of pre-industrial, take a look at this graph. That puts us right here where my cursor is, which means the last 10,000 years have been 1 to 3 degrees C warmer than now.
Yep.
And they're claiming that this is the hottest year ever, and next year is going to be the hottest year ever.
Gee, I wonder if this video is going to get demonetized on YouTube.
Oh, thanks for ruining my day.
It was bound to happen at some point.
So I think what you should get out of this is natural climate variability is king. Mauna Loa CO2. And here is going to be the nail in the coffin. Any of these graphs. So what we've been taxed for and lied to about is carbon dioxide is our fault, and it's warming the earth. The only problem is when you look at the graph on the left, CO2 is controlled by the season and plants. It goes up in the summer and goes down in the winter when plants go to sleep. Well, and this is the earth breathing. Now, since 1960, CO2 has been rising at a constant rate, regardless of anything we've done. There has been no change in atmospheric CO2. And that is because, and this is the big disconnect, humans are responsible for almost none of the global CO2.
But yet you're being told that you should stop breathing.
It's the oceans that control it. Over 85% of all the CO2 is controlled by the ocean, and there is nothing humans could do. Even if we stop all of our CO2 production on Earth, this chart is going to continue to rise until Earth's temperature falls, and then a few hundred years later, it will start falling.
Yeah.
It's the way CO2 works.
Yeah.
To claim any different is to be disingenuous about science, physics, and the data that we're looking at.
Yeah.
Think of how many climate summits have occurred in the last 2 decades. How much reduction. We even have COVID in here where almost all CO2 stopped by like 50%. There's no change in the graph because CO2 is controlled by the earth, not by man.
Right. Well, it's like it reminds me a little bit of that silly article that was like discovering that rocks off gas, large amounts of CO2, and it's like, okay, well, so what? What are you going to do? You're going to ban the rocks now? Like, that's part of the background noise. Like, that's so stupid.
Ban the rocks, folks, and watch the replay on Magnetic Reversal News tonight at 8 p.m.
That's Mountain Time.
On YouTube.
Radio at freedomslips.com. And we'll be right back after this message.